So Adam is a product development engineer with nearly 30 years of experience in all facets of programmable logic product development at Intel. He's worked on all varieties of programmable logic devices, from CPLDs, FPGAs, structured ASICs, and tiles. He's currently responsibility is DFT, test architecture, and manufacturing strategies for Intel's emerging product families. Welcome, Adam.
Thank you, Abram. It's good to be here. Good morning, afternoon, evening to everybody. So today I'm going to focus on kind of a high-level view of chip-to-chip interface testing. And there's a lot of great presentations today on kind of the deep dive technical aspects of things. We have quite a bit of experience with a whole range of combinations of mother chips and tiles. So we have quite a bit of experience with kind of the technical issues we've actually run into from a practical standpoint. And then also the business partnerships that we have in order to get these chips to market. So I'm going to talk briefly, kind of take you on a little journey through the FPGA multi-chip variations. One thing that's important and that I run across a lot when I'm dealing with internal teams is the types of development partnerships there are. So I'm going to go through that so people can begin to segregate what type of partnerships there are when we do these multi-chip designs and what kind of pathologies root themselves in the different types of partnerships, the different things you need to pay attention to depending on the dynamics. I have a few of the key challenges. The challenges, the names have been changed to protect the innocent, but each of these challenges I have I have real experience. The team has real experience with these issues. So these all sprung forth from real issues we had with our multi-chip devices. Calls to action. What are the areas that I need this team to think about, and then a conclusion. What does this mean to our customers, and what are the most important things we need to focus on. So for FPGA applications, I thought this picture actually kind of looked like a Hubble telescope view that kind of evoked the many galaxies in the universe. But these are again simplified to these are all publicly available parts, but we have several dozen multi-chip products within the PSG family within Intel. 6 or 7 different tiles. We have HBM. We have application-specific tiles that were designed from by other vendors. FPGAs are a magnet for chiplet integration. The main thing there is they're quite forgiving as a mother chip. So we have the ability to kind of wrench on the logic if there's an issue. We focused on the tiles within Intel and PSG. We were already experts at fungible I/O, so kind of a fungible real-time I/O where you can address different standards with the same silicon was again as a pretty common FPGA application. And again, the I/O scale differently with the processes, so it made a lot of sense to break those off into separate tiles. The product benefits for our customer, of course, are cost reduction path. So it allows us to chop tiles, use lower cost mother FPGAs. So we often will, for our customer, attach the same tiles to a smaller mother die, or cut off tiles. If someone only needs 2 tiles instead of 4. And then one thing too is it really reduces the risk to our customers by allowing us to have a known good buses between the families. The high-speed analog is tricky. So if you're doing a new logic chip and a new high-speed analog, again, you're injecting 2 high-risk designs into the part. So it gives us a lot of make before break capability, so customers can actually drop a known good silicon interface into their systems, and then they only have to worry about bringing up the new tile. So I've kind of called out, and this is internally, this is one of my codas. When we're looking at how we develop, we're really in the single vendor co-design stage now. So that's the majority of our effort. Again, the issue here from a manufacturing point of view is it bends towards proprietary testing. it makes a lot of sense, right? You need to bring the technology online. You need a focused team that's collaborating, and finding out all the nits so that both sides of the multi-chip module path, again, we have experts on both sides that are both driving towards the same goal of getting a product to the customer. Of course, with no established standard, what we found is it evolves into a closed ecosystem from a test and manufacturing point of view. And currently, we probably have 4 or 5 different chip-to-chip mechanisms based on when the chip, when we designed a chip. And so we're probably on our 3rd generation of chip-to-chip testing on our single vendor co-design. The next is the multiple vendor co-design. So we're taking some steps in this direction. Even internally, we have a pretty close relationship with the internal design teams. Within Intel, it's large, so again, there might be a completely separate team designing a tile, but it's still, I can still call them every day and make sure that they're aligned, that we're aligned on a test and manufacturing strategy. We have at least 2 or 3 different instances where we're now working with external vendors, and we're getting some steps towards a heterogeneous ecosystem. What is important though is there's a lot of there's a lot of coordination that goes on, and people get so excited from the architecture and design point of view that they tend to forget the manufacturing step in specifying a new product. So and again, it's still tending towards, it's still tending towards a proprietary ecosystem where we tell again, there's kind of the mother chip, and then the tiles, we tell the tiles what to do. So the third area, and again, we're just taking baby steps into this area with the CHIPS Alliance, is a la carte. To do this, we need a durable, standardized test approach. So again, like I said, with our single vendor co-design, we have these proprietary approaches. And to be honest, they're clever, but I mean, again, nobody in the test arena is going to look at that and go, "Wow, that is that's a trade secret," right? I mean, we're saying, so we need to kind of open up and decide, what is proprietary and is a trade secret, and what is something that needs to be known to the ecosystem in order for us to have a heterogeneous environment that actually sticks together. And again, what we want is persistence. That everybody's doing the same thing, and backwards compatibility. Again, currently, I'll talk about it a little later, we're actually integrating tiles into, we are designing new mother dice that are integrating tiles that are 3 or 4 years old. So, again, we have live examples of where we're integrating, kind of legacy tiles into brand new designs. Anything in the Q&A, Abram?
Not yet.
All righty. So what are the challenges? So, what are the issues? What are the things about chip-to-chip timing? Is, again, I think it's a reasonably unique DFX challenge. It's a system-level test between 2 separate chips, during package unit test. So again, the classic, kind of the I/O and an interblock design is on the left. So in an FPGA product or any product, we have some type of analog testing scheme for the external drivers and a tester that we can attach to it. Now, whether or not we touch each of those pins at HBM is up to the cost profile of the product, but we can get to them all, right? So if I need to figure out what's wrong, I can go on a bench, I can go on a tester, and I can go look at those pins. And there is again, a huge amount of analog BIST out there that we use in order to validate our IOs. From a logic point of view, internally on the chip, we have X test, right? So we are able to do a border sealing test between block A and block B to figure out, do we have a good logical connection? Again, you can do that at speed. And these are both known approaches to, how we handle these things. So, any DFX team is going to kind of put this on their list of things they need to do if they're, again, doing, designing an IO or, abutting 2 blocks together. So, at the system level, one of the things we need to do is we need to combine these things from multiple vendors and make sure these chips can talk to each other. So, again, we end up, needing to figure out, hey, once we take these, and again, like all components, the chip designers think about their chip. They're thinking a little bit about how it integrates into the system, but that's not always a primary concern with all the challenges of getting a semiconductor product developed and delivered. So ultimately, we need to figure out, well, how do we establish a baseline DFX, and then how do we control it? And we'll talk a little bit later about, hey, what's wrong? When something doesn't work, and it often doesn't work. Again, no matter what the final target is for yield on these interfaces, there's problems, right? Things go wrong. Things end up off target. You get a dirty assembly process, and you have to recover that yield. So there's no, cross your fingers and hope it does, hope this yields 100%, because it doesn't. So what did the other, again, what I talked about is, maintaining manufacturing alignment over a decade. So FPGAs are a particularly long life cycle. So we are actually constantly learning and trying to drive cost out of the product. And we also, as we advance, so we might have a tile that's 3 years old, that we're integrating with, something we're designing in 2022, but we'll also have new tiles that are coming out in parallel to that mother die. And we want to make sure that, we're able to advance the art. So one of the things when people talk about, again, Lego is Lego has a standard interface. But when people talk about assembling chips as Lego toys, it's important to point out that the Lego interface hasn't changed for like 60 years. So that's not really the model we want, right? We're going to continually improve, our test capability, and we're also going to continue to scale the scales towards more density, which is going to require more aggressive testing. So it is important that we're able to attach the old chips and integrate new chips. And Abram brought this up in some of our early discussions. It's very much like the standard problem we've had forever with I/O interfaces, right? You need to make FPGAs always have 3.3 volt I/Os somewhere that we have to constantly maintain backwards compatibility to. So we need to keep that keep that in mind as we're designing. How do we, are we keeping in mind all the tiles we want to integrate? Do we have the test capability? Because at this point, again, the tile environment is pretty heterogeneous, right? So the different tiles have different approaches. Within Intel, again, we might have half a dozen different approaches to chip testing. And again, we're working towards, converging on that, but that you don't do that in a year. And the other thing to keep in mind is the chiplets have a lifetimes that are equivalent to any typical component. The one thing I point out is as much as we want to think we have a co-design, the last time we co-designed a die and a chiplet, a parent and a child, was 6 years ago. So all other improvements, since then we've been making incremental improvements. Not necessarily incremental, but aggregate improvements to our initial test design. And this is, again, sanitized somewhat, but this is kind of our real tile mother die combination, rollout. This is a reflection of a real schedule of our mother dice and tile dice. And again, we mix and match these. We can mix and match any tile with any base die. So one thing that's important too, and this happens a lot, is mine, yours, ours. So how do we root cause the problems? The root causing problems is significantly more difficult to disposition across vendors than discrete components. The one thing that's important, and again, when we think about multi-chip modules, what we're doing is we're integrating and taking over a lot of the PCB board capability. But if you think about it, there's a lot of there's a lot of good contracts, whether they're written down or not, but there's a good partitioning of the responsibilities on a PCB. So each vendor is responsible for PVD DPM coverage on their components, right? So there's no, well, we gave you a known good die and it runs it hot, and we don't know if it runs it cold, so we need to do a cold class test or a unit test. The vendors are responsible for qual, so that's a big deal. So again, qual, reliability qual are is with these big packages and these different types of connections, it's a big deal. Customers really want those qual numbers. The PCB is a demilitarized zone, so if whether it's Intel and Micron, we agree that the PCB is a valid interface between our chips, and as long as the PCB company hits its targets, then our chips should work together. Well-defined component-to-component interface standards. So again, there's no argument on what DDR means. Again, there's 8,000 pages defining that particular spec, and there's clear quality criteria for each vendor in the system. So there's no disagreement to what So if if chip A bubbles on your board, you can go talk to the chip A vendor. If tile A bubbles in your MCP, well, it's not quite as clear. Is it packaged? Is it the interface standards? Is it the did the mother chip use the tile incorrectly? So again, these clear quality criteria for each vendor. Again, it's partitioning and requiring that each vendor have a certain quality level. Again, in a heterogeneous integration, our vendors can only just screen to the discrete die level. Again, package integrator. The package integration qual becomes the integrator's task. Again, the PCB DMZ is replaced by the packaging technology. So the interpackage IO interfaces are in their in their infancy still. Again, there's still a lot of innovation going on there. And then there's quality criteria is incomplete for the chiplets delivered to the integrator. So again, what we find is, there is a lot of confusion as to who owns the qual, and it's hard to own the qual on a chip you didn't design, right? Because it's hard to figure out what went wrong. So what do we need? So what's the call to action from this team? And again, I'm not naive. I understand, these things are hard, and folks, have their preferences on how things should be done. But this is my view of what needs to be done if we're driving towards a heterogeneous ecosystem. So we need the full recognition that C2C DFX requires system level coordination early. So this is a significant problem in our MCPs. Again, even it gets tangled quite quickly, trying to figure out, hey, what's the test content? What's our test access? Chip A wants to use, one full chip JTAG, concurrent standard. The other, the legacy chip uses some, other scheme. It's annoying, right? So, and it causes a lot of confusion. Again, these problems are solvable, but if we want to do things rapidly, we really need to look at these little details and smooth them out. We have to understand, how do we standardize the BIST? Again, the very first external standard we tried to put in place for interchip for an interchip hard macro, or for an AIB hard macro, they forgot to put the test requirements in. So we had to go back and we put them in. So we need to make sure that as we're defining these things, both the tile and the parent chip respect the fact that there has to be some investment here to make sure it succeeds. The other thing that's important is, hey, if you have a legacy chip, that's it. If I have a legacy tile, I need to conform to that tile's interchip testing capability if I want to use that tile. And that goes to backwards compatibility. The age-old siren, it's not a siren song, but the standardized test access. So we're getting test content from other vendors now. That's being brought up on different testers. That's being brought up, in different environments, and we're getting a tarball shot to us to run on our own tester in a different topology. So we need to figure out, well, how do we standardize this test access and the handoff? Failure isolation capability is incredibly important, right? We need to be able to say, hey, you know what, your chip isn't working, or hey, assembly house, your chip to chip interface is not working right, or we're steering the tile wrong. It's extremely important, and these things get complicated, right? So you have 3 or 4 vendors in the loop, and it takes months to figure out these issues, and that's no good for our customers, right? So this is more, my first line of defense is always, being a test engineer and a PDE, a product development engineer for my whole career. It's like, how do I make my life easier? But it makes the customer's life easier. If it takes 6 months to figure out why something's not working, I have a very unhappy customer for 6 months. Security and test need to play well together. So that's an area that I think a lot of PhD and theses will be written on. Security and test, again, they don't play well together on a normal chip, let alone this physical interface. So the one thing to keep in mind is this is considered a physical interface, and customers are very aggressive about how this is protected when they're doing proprietary activities between the 2 chips. So it's a leading question for security experts when they come in from the customer. And again, we need to avoid what I call the panic room approach, which is shut everything down once it becomes a production chip, because then it makes it impossible to test that chip or to do FA on it. So we need to think about that. And again, I don't think that's any different than what we do with a lot of the chips. With any chip. And then, I say overinvest instead of underinvest, right? So let's get in front of this, right? And within Intel, we've done this. We've set up a really good, from what I've seen from broader Intel, there's, a lot of investment, and you'll see Srijit talk a little bit about that. And, within the PSG and FPGA community, they call us first. Again, the first tile, they called us last. They go, hey, how are we going to test this? But now we get in right at the beginning, and there is, we worked hard to say, hey, don't cut corners here, because, it's one of those places, if we're careless and we cannot validate this interface, then we are going to have some unhappy customers. And it's really hard to go probe these, if not impossible, to go probe these signals to figure out what's wrong. So let's think about, again, chiplets are kind of crawling out of the primordial soup of the semiconductor design process right now. But, how do we develop chiplets like components? So the chiplet needs to be a full-blown product. This means documentation, chip-to-chip interface characterization, and qual. So if you're making a chiplet, you need to think of these things. It's not just an FPGA design where you do the RTL and splatter it out to a tile and hope that, everything sticks together, well. We need to define what our common, product lifecycle parameters are: cost, lifetime, DPM. We need to think about that. Again, FPGAs, have a long life cycle, and we need our tiles to think about that. Because again, a good example of that is HBM. Is our life cycles off from the DRAM stacks. So oftentimes we have to go, think about, hey, how do we requal a stack to continue delivering the product? Again, it's fine, but it's better to know ahead of time. I see the other Adam, one of the other Adams in the test community is here. The CAD ecosystem support integration and common system level understanding among vendors and the customer, because we need to convince the customer we're able to drive down into these details. Good contracts make good partners. Make sure that the negotiations include manufacturing. Again, maybe it goes without saying, but pretty often we found that oftentimes when we use a third party, they're not thinking about this. Design houses are not usually started by the manufacturing engineer. They're started by the architects. So get in there early and make sure we've established this as a baseline for any new partnership. Again, standardized inter-vendor handoffs, develop C2C interface and standards with the same rigor and robustness as intercomponent protocols. So again, think of how much investment goes into the I/O standards we use on the chip. The TX, the RX characterization, how it plays with different PCB layouts. Again, what are the PCB parameters? I mean, billions of dollars go into that. Maybe not billions, hundreds of millions of dollars go into getting those standards set up. Coming from Altera originally, like seeing the amount of investment that Intel puts into PCI Express stability was staggering. It's awesome because it made our PCI Express way better. But I mean, there's a huge investment going into that, and now we're like, it's just a couple IOs that talk across the, some chip-to-chip interface that somebody else is, designing and manufacturing for us. So we need to think about that. Again, think about a life cycle. And the one thing that's happening is, again, eye is bigger than stomach. We need an accretive approach, and we need to avoid too much too soon. So, we talk about going from a few thousand EMIBs on some products now, chip-to-chip interfaces to several 100,000. That's in the future, right? That can't be next year. Getting to the root of the problem, and again, this is so critical for the customer. And again, it's we all know that siting and failure isolation starts at the architecture level. We need rapid vendor level failure analysis capability and service level agreements on debug. When I have an issue, I need to be able to, get everybody in a room and drill down into what, the problem is. And I've seen this work well, and I've seen this work well. We've had and HBM's a good example of, I think a pretty well sussed out spec. And when we had issues, we could, we had a common 93K platform that we can go and check things out. I mean, it took a huge amount of investment, but there is some precedence for a good service level agreement on debug and be able to pull the vendors together. Sorry, I put the same thing twice there. Controlling debug turnaround time among vendors on products of differing maturity. Again, if I have a 3-year-old tile, those designers are long gone. Right. So we need to be able to, pull, if you have a tile, that you're sticking to a new mother die, you need to be able to call the vendors in and get the debug going, on a product that might not have been opened up in a couple of years. Again, one thing, I might do just for fun is, hey, how do we compare and contrast the PCB system debug model? And again, I think PCB system debug benefits a lot from good partitioning of qualification. Again, I have a well-known interconnect process in PCB manufacturing. I have well-qualified devices and components on the chip that each vendor, puts a lot of investment into stabilizing. So we need to think about, how does the PCB system, compare to what we're building? Again, robust design, again, overinvest instead of underinvest. Make sure we invest in DFM. Design for, test, manufacturing, debug. We need to think a little bit about, investment in physical isolation. How do we do physical checking faster? And then, and again, this, getting to the root of the problem, again, we'll have integrators, different chips and heterogeneous permutations that we have to go and debug. So it's super important that we get these things lined up, so we're not scratching our head going, hey, we have some buried interface, we have no capability to characterize, figure out what's wrong. And again, that doesn't mean, again, everything plays well together. If I have an error somewhere in my manufacturing stack, I'm going to need to lean on the other vendors to help me point to what is right and what is wrong. So, again, I think the call, again, these are, again, my thoughts and issues that we've run into with our multi-chip modules. The bottom line is what we want to do is ensure that our customer succeeds. We're replacing an established integration model, and we really need to take understand the challenge we're taking for the board and system design, and what we're taking on as an integrator, and understand there's costs associated with that. So a lot of times there's arguments over what we need to do. It's because we're taking on extra work by integrating these things, and it's a different model. If I'm integrating functions into silicon, well, that's a well understood problem, in the fab and product design. As we're taking designs in silicon from different vendors and sticking them together within a package, that is a completely different model. Again, we're relying a lot on the capabilities of other vendors to make sure our system comes together well. Designing in quality, is the bedrock foundation of semiconductor and system success. I think one thing that the EMIBs, again, we'll use EMIBs, chip-to-chip issue, chip-to-chip seems like a simple test problem. So it's easy to kind of talk away like, just a wire running at a reasonably slow speed. But you need to think about it. There's a lot of those wires. There's redundancy. There's a lot of signal integrity. There's a lot of signal integrity considerations you need to take into view. So we really need to get together the BKMs for the foundation for our chip-to-chip testing. So again, continuous improvement to ensure quality early and often is a large investment. So again, with our initial chip-to-chip designs way back when, 5 years ago, that there was a huge amount of continuous improvement at the beginning of the process, which we hadn't counted, right? Because everybody said, it'll be fine. It's a zero yield loss operation, and it wasn't. So, just keep this in mind that there is a huge investment to getting these things connected, and it's an investment that as an integrator and a product vendor, we're not used to having to handle. And again, the rallying cry of every product development and test engineer is, hey, we need this investment in quality upfront, and we also need observability to drive effective cost reduction and quality assurance. So again, it's a two-pronged investment. It allows us to get a better product to the customer, and it allows us to drive cost reduction more quickly. So, again, my final thoughts here are, back to 1% inspiration, 99% perspiration. So it's easy to imagine this as Legos. It's hard to figure out, well, how do I have a Lego? How do I establish what that interface is? How do I manufacture it to a level of repeatability that allows interoperability? And also, how do I extend that as the technology improves? So to move to a manufactural mix and match heterogeneous ecosystem, again, I don't think anybody disagrees with it. It requires a significant investment from both a technical and business perspective. And again, given that this is silicon, it's not like you can make a mistake and fix it. Kind of the FPGA fallacy. Once it doesn't work, you have to respin those masks. Again, this has been my rallying cry for 30 years is overinvest in test, debug, and failure isolation for these buried interfaces. And again, think about it in terms of the investment we have for other standard genres of circuits. MBIST, ATPG, again, to talk, targeted at Adam Crone, is how do we set up a standard for this testing, so we can get to the level of manufacturing efficiency we have with MBIST and ATPG. And IOs are a little different, but again, there's certainly nobody would argue there's not a large investment in test standardization for analog IOs. And again, we need to decide if we're if we want this heterogeneous ecosystem. Not my call, but again, I think that's what we're trying to do here, and that's going to require that we collaborate. So forums like this, all the vendors, including us, need to decide that, hey, we're going to share these ideas and drive to a common solution, and also not just the least common denominator, right? These things have to improve, and we can't just rely on what we invented 5 years ago to carry us for the next 5. All right, thank you, everybody. I appreciate the time this morning. Hopefully you found this interesting. Anything in the Q&A, my friend, Abram?
Actually, yeah. Thanks, Adam. I know we're running a little low on time, but if we could maybe have one question, possibly. So one of the questions here in the chat is, should probing on pads or bumps be pushed for chiplets? Pads can help with chiplet integration, packaging platform agnostic to some extent, but probing on the bumps can make the design happy. So any preferences or anything that you're seeing?
So it's always been a heavy lift to get extra pads and probes. So we've definitely looked at that, but for the most part, we in the PSG realm with the FPGAs, we don't typically do that. I don't know, at broader Intel if that's a standard approach, but yeah, we don't typically add test only pads to look at things. So I mean, we already have issues with getting enough probes, into the area. Adding extra pads is that's a heavy lift.
Yeah. All right. Great. All right. Thanks, Adam.
All right. Thanks, everybody.
I want to thank our sponsors once again who made this event possible and free of charge for everyone. So thank you to the sponsors. And if you have an opportunity to thank them when you are in contact with them, it is greatly appreciated so that they will continue to sponsor events. Walking through the sponsors, first and foremost is our diamond sponsor, Amkor, with their differentiators in technology, quality, and service. And in the emerald sponsors, we have Advantest with the highest rankings from VLSI Research, and Synopsys Silicon to Software. We'd also like to thank our Ruby sponsor, TechSearch International. And most importantly, we'd like to thank all of you for attending today, and I look forward to having everybody back tomorrow. So thank you and have a good rest of your day.